Amy is not here. Yeah. Oh, that's right. She traveled. All right. Each strand is 0.16 diameter. They want to know what the factor of safety is. And then they give us this ultimate stress, right? Ultimate stress of 230 KSI. If you're given a stress, you use it. So like Devin said, we don't usually use the ultimate stress, do we? No, not normally. But this would be an inelastic design, meaning that somewhere one of these strands might go over the limit, but most of the strands are going to be fine. Somebody above our pay grade said, do the factor of safety to that number. So that's what we do, factor of safety to that number. So we need another number to do factor of safety. We need the stress, right? The calculated stress based on this load, those strands, and that area. Yeah? Yeah. And I would maybe write down calc just so it's different than ultimate. Like this is the stress based on the load and the area. We'll get other stresses that might be based on Young's modulus and strain or something, right? But this is actually a calculated stress from P over A. So P being 2.6 e to the 6 pounds. You could probably go into kips for that to get it to KSI, so we have a good comparison, but I'll just leave it that way. Actually, I can just erase the 6 and make it a 3. And now we're kips. And then the area is going to be this area, pi 0.16 squared over 4, pi d squared over 4, that's d, times 1470. Yeah? What'd you get? Anybody get? Anybody want to say what they got? Okay, so cool. Perfect. I trust you. Remember, it's therapy for me to run my calculator. And I need therapy all the time. Yeah, same number. 87.968 KSI. So then it would be a comparison between that failure and the calculator. So failure's on top always. So we take the 230 and divide by the 87. And we get 3.63, factor of safety. 3.63. You rarely see it like in a decimal form. It's like factor of safety of 3, factor of safety of 4. But yeah, that's what it would be, 3.63. And that would be to failure. So sometimes the design is okay to go to failure. Like, hey, we can design this all the way out to fail. If it breaks, no one's going to die. I wouldn't think that's the case on this creature, but they do have their ways of doing it to the ultimate, calculating the factor of safety.
Factor of safety ever come in units, or is it always a hard number?
It's always a hard number. It's usually unitless, and it's most often done with the stresses. I don't like to do it with the loads. Like you could calculate, you could reverse calculate this and say, hey, I know the area, correct? Here's the area. And I know the load. And I know this ultimate, right? So if I use the ultimate and the area, I could get a ultimate load. Agreed? Like it would be stress and area. I could get load. And it's going to be actually 3.63 times bigger than this would be that failure load. Then you could take the two loads and get the factor of safety. That's just typically not the way it's done. You can do it that way. It's just not great to show it that way. It's better to compare the stresses to get factor of safety. But the book did have that 1P equation for factor of safety. So they must think it's okay to do it times. All right, great. Then this one said we have a 6-inch diameter. It's concrete. Is that right? Yep, 12 inches tall, and we're given this, the 0.0029. I think they called it total elongation, right? It's the change. We're given a load 20,000 when this reading is taken. So somehow they measured this, and we have these two things happening at the same time, and they want to know E. So the relationship for E that we know is stress over strain, right? And stress is equal to, what's the equation for stress? P over A. You're all thinking strain. I was going for stress, which I'm gonna do that all the time because it's gonna be like, oh, your brain's gonna be like jumbled. Now, as you just said, what is strain? Change over L. Yeah. So you will see this in this form, right? Very common. And E equals PL over AE. It's so common that I have that one memorized too. Like PL over AE, we use it all the time. And it's essentially P over A, stress, over strain, and it's reversed here because, right, we have to flip this up and do our algebra shenanigans. So this we use quite a bit. If we know the area and we know the length original and we know P, why did I put that in there? Sorry, delta. Right, delta's here down below, L flips up and A is already down below, so it stays there. There, PL over A delta. So if we know all these, we can get the modulus. And this is exactly what we do when we do concrete testing. So if we want to know the modulus elasticity of a run of concrete, like if you were building this place, there is so much concrete here, you have to know what you're getting. So they will send you test specimens when you buy like hundreds and hundreds of yards of concrete and you request the test specimens. They will make a run of concrete. They'll pour the little test specimens that are about this size. And then you'll get those when they deliver the concrete to make all these pours. And you'll be able to run the test and say, yep, you mixed it right, people, because that's important for this kind of structure, right? Not really. Like
you can't like.
E for concrete is pretty big number and it's going to come in that pocket somewhere. I mean, it's never exact, but if you get a bad mix, E's way off, like, so you'll know right away. Yeah. So you can also get like, if I was to call up Schnitzer Steel and say, I need, 14 truckloads of W shape because I'm building a bridge, you can say, and I need material specifications for that material. They'll send you the test specimens for that material. And then you can run your own test and get your own modulus elasticity, Poisson's ratio, and a few other material properties that you can get from running a test. So you can verify that if you need to, if like your design is critical, then you would need to do that, right? So bridge companies do that all the time, but on smaller projects like home residential, you don't do a concrete test on your concrete. You order 2,500 PSI concrete, you get that. And if it's a little off, the house will be fine. Concrete's way strong. You're not loading it at all. All right, so then we would put it in. I'm gonna slide down just a little, 20,000 pounds. Its original length is 12 inches. Its area is pi 6 squared over 4. And the change was 0.0029.
Adjusted to 36 to keep everything in inches, or is that not right?
This is 6 inches.
Oh, okay.
Sorry. My scribbling. Right? Did I misread that? Let's verify. Yeah, 6 inch in diameter. So 20,000 12 times. I get 2.93 e to the 6. And I'm guessing it's in KSI. So it would be, why can't I do it? That's PSI, right? So 2930 KSI. Why does that number not sound great? What is concrete? 3120. No, that's modular elasticity. Yeah, that's what we want. So one's 3120, one's 3605. And we are getting, did you get 2930?
I got, it's there. 2926. Yeah, I got 2926.
Yeah, 292698, right? Yeah, so I rounded maybe a little too much. So maybe 2927. Still, it's off of the 3120 quite a bit. So that would not be close enough. But that would be the modulus elasticity of that test that they ran. Yeah, perfect. So again, that's only valid if we are within the stress levels. But since that modulus came in under, I would guess we are. But we could do that quick calculation, right? P over A would be the stress. So 20,000, right? Divided by that area. Gives me 707 PSI. So yeah, not very loaded. .707 PSI. There is no yield strength for concrete. There is 0.3 and 0.4 KSI. So it's way under. It might be why they're not getting a good modulus. They didn't load it enough. So if you load it more, it just gives you, you'll see when we do our tensile test, the more you load it, the better deformation you're going to get, probably the better reading you would get. So, but yeah, this concrete is not wonderful. Good? Excellent. All right. So now we're going to talk about the curve, which I kind of wish we would have talked about earlier, but it's hard to know what order to talk about things. Because now you have a little bit of feel for the stress thing. You have a little feel for the yielding of a material. And this chapter is all about like what materials can do and their properties, right? So when we talk about the stress, strain curve, this is the curve that gets created when we test a material and get its material properties with something like this, typically. Wood's a little different. We don't use these kind of specimens, but almost all metals of any kind, we use this kind of specimen. Concrete, we do the compression testing because concrete doesn't stretch very well at all. So what they do is they take a material and they load it up in a test machine. Looks something like, I'm not going to run this yet.
First test, material with yield points.
Cool.
In the first.
So this is the machine. And here's where the test piece goes. They're fairly robust, so you can test things like titanium and things like that. They got to be pretty strong. Our little tester next door, you can put titanium in there and jack on it all you want. It ain't going to do anything. It's not going to do it. So we don't test that, but we can do mild steel, aluminum, brass, copper, all those kind of things, right? So, I mean, there's companies that exist to do just this for you. So that's cool. But what they do is they load this thing up, right? It's got threads top and bottom. Actually, they're all a little different. I have some other test specimens next door. And it creates, as you put load on it, and I'm going to write this in the form of stress and strain. Remember, strain is essentially change in length, right? And stress is essentially load, because it's P over A, and this is delta over L. So what's happening, and the area doesn't change, right? The test specimen is the test specimen. The area is the area. It actually, as it stretches, it starts to change, right? But in the elastic region, that change is small enough that we don't have to really like recalculate every time the diameter changes. So really, the curve is also just load and stretch. That's what's going on. As you load something, it stretches, right? So in the beginning of the load and the stretch, oh, there it is. It's a linear relationship. Linear means straight line. As you give it more load, it stretches more. As you take the load off, it goes back a little, right? So in the beginning, and when I say the beginning, this thing has a life, right? Because we're going to jack on it until it does this, breaks. So it has a life, just like materials have lives. In the beginning of its life, that relationship is linear. That's the elastic region. We want to work in this straight line region, okay? So this curve is for yield phenomenon, I think is what she called it, right? But it's for elastic materials, and not all materials are elastic. Some will not make this curve. So it goes up until it hits a certain point, and then it just slightly curls over. In other words, in this region, we're adding load, we're trying to add load, or we just let it sit there, and it stretches, just kind of continues to stretch under that load. Like you're really close to permanent yielding, you might even be there. And this is what we call our yield. Yield stress. So when we look up yield stress, that's where it is on the graph, right? And it actually like dips a little, you'll see. I'm going to exaggerate it. And this is sometimes called the lower yield point. We don't really use it, but that's what it's called. And then this crazy material, if it's mild steel, does this. It actually gets harder. It can all of a sudden take more load, more load, more load. Super cool. At this point, though, it is no longer mild steel. It is changing its molecular structure. It's becoming more brittle, but stronger. Not great. Brittle's not great for what we want, right? So that's why we don't work in this region. We work in this region where it's going, stretching, coming back. It's all good, right? And then over here is ultimate. So this region is called strain hardening. So that means it's being strained, which means it's stretching, but it's actually getting harder. So the materials that demonstrate this phenomenon are great engineering materials. We love them. Aluminum does it. Aluminum's is like a lot more stretched out because it's a lot stretchier. So it's just flatter. Take this whole graph and kind of roll it and stretch it. That's aluminum. Titanium, that's its full curve. Like carries a load, doesn't stretch much, right? This is stretch, doesn't stretch much, and then blows up. No warning. Super strong, super light. We love it, but doesn't give us these characteristics. Okay. When you get into this region, anything past here, I can put a little dotted line. This is in the book. This is elastic. Meaning it stretches and comes back. You put this load on it, you get that much deformation, you let go of it, it comes right back to zero. In other words, it goes back to its shape. Anything past the yield, we are plastic. The plastic region, meaning when you stretch plastic, it's done, like it can't come back, right? That's what plastic does. In this region, in the test piece, you'll see visible area reduction. It's called necking. And if you look closely at my piece, I have stretched this one. Do you see the necking? Yeah. You also get fish scaling because I said in this region past the yield. I get it all. Oh, I can. That's cool. This is where necking occurs. This is where it's strain hardening. This is where it's no longer the material that you started with. It's different. You get fish scaling. The surface actually changes. So you can see this is kind of dull, a little bit kind of, it used to be shiny like that. And it has begun to fish scale. It's changing phase. It's no longer that earlier material. And the area is reducing, which we know when area reduces, stresses go way up. This is like seconds before. I can't always stop on our machine because you can't load it slow enough. So this one I was able to like just keep sneaking up on it, and then we all saw it, and I said, "Oh, we got to stop and save this one because we can get this anytime, right? We'll bust ours today." So there you can see necking and then a little flare and then the failure, right? That's that. Focus on it, probably not. Anyway, it's a very, very brittle material inside there. You can look at these. Elastic material starts elastic and then it necks and then it becomes very brittle. Right? So that's the graph. That's how we get our material properties that are in that table in the back of the book. Young's modulus, the relationship between stress and strain, right? That's here, anywhere in there. So if I go here and here, there's a stress, there's a strain, a strain. That is Young's modulus, that relationship between stress and strain. You can calculate it anywhere along the straight line and get Young's modulus. You cannot calculate it out here. It is called the modulus of elasticity. That's why it's in the elastic region. But Poisson's ratio, which we haven't talked about yet, and a bunch of other properties we get from this test. That's how we get it. Would we get the same way? We just do it different with different specimens and different testing. All right. So let's check out this video. It's a better test than mine, so thought we'd watch it.
Tensile test, a plain carbon steel with viewpoint phenomena to be tested. This is the test piece. It has a cylindrical test region with an original diameter of 10 millimeters and an original gauge length of 100 millimeters. Within this test region, distance marks have been drawn at regular intervals. They help to visualize and measure the plastic behavior of the specimen. Using a hand control, the tester moves the upper crosshead into its correct starting position.
It's a pretty big guy.
Now we can place the threaded ends of the test piece in the lower and upper grips of the testing machine. In the next step, he swings the extensometer into its working position and checks that everything is correctly prepared.
We have a much smaller.
Then he selects all necessary testing parameters on the control computer.
That's just measuring the information, right? Because the machine will do the load.
The test starts and the extensometer's sensor arms are carefully pressed onto the test piece. This way, the gauge length can be measured throughout the whole tensile test. The gauge length is displayed at the bottom right-hand corner of the screen. At the beginning, it amounts to 100 millimeters. During the tensile test, the test piece is slowly and constantly elongated with a standardized speed. The force that the test piece opposes to the imposed elongation is recorded and can be seen at the bottom left-hand corner of the
They're
computer
doing
display.
kilonewtons, right?
The
It's all
material
metric.
behavior can best be observed in the force elongation diagram. The force F is being plotted upwards on the vertical axis.
This
The
just started to
elevation
move.
delta L towards the right on
Stretch.
the horizontal axis. At first, the force rises rapidly. Force and elongation are proportional and form a steep, straight line in the diagram. In this area, the material behaves elastically. If the test piece were to be unloaded from this area, it would spring back completely to its original length. In materials with yield point phenomenon, the end of the elastic area can be seen clearly. The plastic deformation starts abruptly and is accompanied by a sudden drop of force. If the test piece were to
So
be
the force
unloaded
is dropping
now,
and it's
it
still
would not
stretching.
spring back to the original length, but instead show a permanent elongation. In the next stage of the tensile test, an almost constant force level with slight fluctuations occurs. This phenomenon is called the Wheeler's effect. After a certain strain, known as the Wheeler strain, the force increases again. The material opposes an increasing force against the imposed elongation. Its strain hardens. Up to the point of maximum force, the test piece is strained uniformly.
How far
along
it
its length.
stretches.
This means that the test piece gets longer and thinner, but keeps a cylindrical shape. As soon as the maximum force is reached, a neck begins to form at one point of the test piece. All further plastic deformation now only takes place at the neck, and eventually the test piece fractures there.
So necking will occur where there's the smallest little imperfection, little carbon pocket, little nick, crack, anything. Boom. That's it.
In the recorded force elongation diagram, the force FEH at the upper unit.
I think she's just going to identify all the parts.
This is the highest F max.
Yeah.
The upper
So
unit
they're using
is
force instead of stress
calculated by dividing the
because the area is the
force
same. Just take the force divided by the area and you can get stress all along there too.
The lower unit strength REL.
So a little different graph than I showed you. That one. But let's see, I think. Chapter, yep, there we go. Their graph's gonna look a lot like my graph because it's just a lot more common. Maybe it's just easier to explain, you know, the parts and pieces of it, but same kind of thing. This is a material that shows a yield. Some materials do not show a yield. I don't think they show any other graphs, but ours doesn't create a graph, obviously. It used to give us load, but then the little load thing went kaput. So now all we can do is break things and watch the elongation, but it's still relatively fun. So I think we should go break something. It's next door.